Okay.
Oh, yeah.
There were elemental abundance.
Yeah, stellar abundance. Mm. Okay. I'll present a paper titled Determining Stellar Elemental Abundance from DC Spectra with Data-Driven Paint by Zhang et al. So the background of this research is that there are many numbers of low abundance survey for Milky Way halo stars, and it observes the spectra of many outskip stars in low resolution in white area. And on the other hand, the high resolution spectra only available in small amounts, which is an example in SDSS apogee, they are 17, which I think observe the star around the Milky Way disk. And there's a problem of line blending between various elements that cause the problem to determine individual elements. Then in this research, they use the DC early data release, which is actually a subset that used for survey validation in the B, R, and Z band spectra at those wavelengths with magnitude range of around 16 and 20 magnitude with 600,000 spectra for around that amount of objects. And the data is available for public at different. The method of this research is using DD-Paint machine learning models of the stellar spectra with two-layer perception neural network. And before using spectra, it cross-matched with Lemos data, which actually metallicity estimation. And the spectra used as training feature and the metal abundance as the label. After matching with Lemos, it has around 3,000 star with signal to noise ratio higher than 20. So we use 90% as the training set and 10% as the test set.
For training set, how did they decide the abundance?
I think they took from certain range of abundance, and then 90% gone to the training, and the test to the 10% of this.
How did they measure the abundance of the training set?
Oh, I think they have plots here. Yeah, they compare with DC, and then for each element, yeah, they plot the value, and then yes, I think it's like the same distribution. Yeah, here's the distribution of the in this example the FA per H, and then it's around here. I think for the selecting the training set, they choose randomly. So they will take what range of abundance.
So the idea is for the high signal to noise ratio, you just measure directly from the spectra and apply that to low SM. Is that how it works?
Yeah.
Okay.
I think yeah. This one is the label cross collision with Lemos that we saw that mostly BSC is agree with Lemos at wide range of uh, elements.
What about chromium? Doesn't look good.
Which one?
That one, chromium.
Chromium. Oh yeah, chromium is seems like chromium is less is more sparse. So I think the result will not be as good as the others.
I'm asking why.
Um, uh, I think there's a physical reason behind it, but I've not yet now.
Which one has a better essence, the most, or what is it?
The better example is the one that fit the red line, which means between Lamos and DC, there's an agreement of certain
No, no,
value.
I'm not asking. My question is,
Oh,
which
okay.
one has better symmetrization, the most or the
Mm, I, I think in this case Lamos, but the sample number is fewer.
no number, symmetrization, I'm asking.
Ah, yeah, that's Lamos because Lamos is designed from chemical abundance.
Okay.
Yeah. And then this is the distribution. Uh, yeah, and this is the result of the training with 10,000 iteration with each epoch using 5 batch and 500 samples. So we can see after 10,000 iteration, the loss value became uh, became less decreasing. So it's stable at one value. And then this is the fitting of the differential spectra between the curves with which is a simulation and this DD plane. And this is the correlation coefficient among label, which is the metal elements, and this is compared to the spectra. So here we can see that effective temperature is very correlated to the spectra. And the result, it produced a catalog of stellar parameters and the abundance of 12 elements, and also estimate the extension and distance as well as the stellar orbital parameters. Here is the result which confirmed with the apogee DR17, which show similar trends. So the red line is the trends of apogee DR17, and those dots are the predicted results of this experiment, which we can see that the yellow area is more dense. And then this is the error plot. So for the effective temperature, I think for all of the labels, it has better accuracy with higher signal to noise ratio.
So this is for machine learning.
Yeah.
Machine learning can also return the error.
Yeah. The error is like the accurate the difference between the actual value and the predicted value. So it's in units index for metallicity.
Okay, so I'm confused. So if you have already accurate value, what's the point of using machine to measure it?
Uh, the actual value is from the simulation. So it's
So this
like
is simulation now?
no, the simulation is like the theoretical value, and then we compare the predicted value from the observation, and then compare the error.
So what is simulation? I'm confused now. What is simulation?
This one, curves. So we use the DD pane as the machine learning experiment and QuickF as the standard benchmark for this. Yeah, I think like that.
Right. So you train machine to tell the abundance from spectra, right?
Yeah.
Why you need the simulation?
From what I get in this paper, it's for the benchmark value. Yeah, but yeah, so far I think that's the only way to know the best value, because if I think if we compare one observation with another observation, there will be greater error. That yeah, I think I need
For the
to.
training sample is data, right? Not simulation, right? Or did they train with
Uh,
simulation?
no, it's the observation.
Then why do you need simulation?
Okay, I need. I think I need to learn more about this because they mentioned about another paper. I think.
Okay.
Yeah, that's a good point. Okay, and then the conclusion in this research, it applied the DD pane to the CADR spectra for the determination of stellar atmospheric parameter and those 12 element abundance, and with spectra with saddle to noise ratio more than 20, it achieving average error of 60 Kelvin in effective temperature, uh, 0.17 in log G, and 0.06 in NTHU, and it observed consistent trend with high resolution but per samples from apogee there 17. Okay, I think that's all from this.
Okay, thank you very much. Questions, comments, please?
Still need to.
Data is low resolution.
Yeah, the data is low
That's
resolution.
why you cannot make it directly.
Yeah.
Okay. So how accurate is it? Is that the
Mm,
sorry? Can you show the accuracy of the machine learning?
uh, the accuracy is on the result part, in the result part, which show the uh, measurement error. So the accuracy will be 100% minus the measurement error.
I'm sorry, accuracy of machine learning data.
Uh,
Result of the test.
wait, why cannot I share my screen? Uh, this one. Yeah, it showed the error of the machine learning. So the accuracy will be,
So
I
this
think,
is from the test sample.
yeah, this is from the.
Okay.
So I think they didn't mention the percentage, but they mentioned the average value of the error. So if we want to convert it to the accuracy, we need to know the average value, and then we subtract it with this measurement error.
Okay. Any other question, comment? I think it's a very good use of machine here. If your resolution is lower enough, so you ask machine to sort of make it higher resolution to recover these old indices. And then it seems, it seems some bright elements it's successful, right? I run on the magnesium,
Yeah.
even SN10 error is very small.
Yeah. Yeah. I think so, for some elements, there are some physical process that it's hard for the machine to learn that what happened inside the stars. So I think for like magnesium,
Why?
they mention it in this paper, but actually I haven't understand about that.
Okay, you're opening kind of worms.
Yeah.
Okay, any other questions? Okay, if not, thank you. Some them. Shall we move on to the next person?
Here.
Okay, please go ahead. Okay. And who are you?
陈思婷.
Cynthia. Okay.
Yeah.
Mary?
Okay.
Go ahead.
Okay. So this paper is one of the research in this magnetic field in massive star-forming regions survey, and this survey is observed 30 high-mass star-forming regions at 1.2 millimeter with the ALMA. And in this paper, they aim to assess magnetic properties and to investigate the importance of the magnetic field, gravity, and turbulence in the star-forming regions G333. So this figure shows the plane of sky magnetic field geometry toward this target, and they obtain after rotating the polarization segment by 90 degrees. So it is a common way to obtain the magnetic field directions. And this color map is ALMA 1.2 millimeter dust continue emission. Position of MM1 and MM2, these two protostars are marked as plus symbol. Okay, maybe not protostar yet, but a dense core. And we in this figure we can see an hourglass-like geometry of the magnetic field aligned with the symmetry axis of the hourglass, almost parallel to the minor axis of the flattened envelope, and it is more clear in the right panel. Yeah, so this is the magnetic field geometry here, and they also observed the H13CO plus line emission. So the upper one is the moment zero map, which is the intensity map, and the lower one is the moment one maps, which shows the velocity gradient. So in this two plot, they see no clear signature of large-scale velocity gradient. The velocity field over MM1 and MM2 is relatively more blue shift in this moment one map. So they think that it is maybe a sign of info motion in this two core. Okay, so then they do the modeling, and with this modeling, they will produce some magnetic field geometry here. So the orange segment shows the magnetic field direction from the modeling, and the green one is from the observation. Okay, they use this dust pole model from ARTIST package, but it's not really important. Like some way to do that. And they found that there is some difference around MM1, and it is possible that the gravity of MM1 will drag and disturb the magnetic field line more effectively than MM2, so which caused this problem. And they what?
Where is this discrepancy? What's the difference?
The direction. The direction.
Where?
Here. Around MM1.
Oh, I see. Green and orange are they're crossing different directions.
Yeah. Yeah. The observation result is different from their modeling, and they think it's because of the gravity of the MM1. Yeah. So then they use this DCF method, which is a common method to estimate the magnetic field strength. And actually, in this method, they will assume the deviation of magnetic field is by turbulence gap motion. And with modeling, they can also consider the gravity. So they will from all the deviation of magnetic field, they will first cut off the part from the gravity and then estimate the magnetic field strength. So the plane of sky magnetic field strength is 4.0 milligauss, and the total one is 5.7 milligauss, which is quite strong. And they also estimate the mass to flux ratio, which is about 1.63, and the turbulence to magnetic energy is 0.66. So the result is that the magnetic field toward G333 is quite strong, but it still could not prevent the fragmentation and eventually the star formation. So they think the collapse happened after the core reached a supercritical mass to flux ratio and leaving behind a considerable amount of magnetic flux, which will help to transport out the angular momentum through strong magnetic braking. And we can look back to this figure 2. So
what's the magnetic field at MM1?
What?
What's the magnetic field strength on MM1?
What's the magnetic field strength on MM1? Oh, they only calculate the total magnetic field strength, like the whole region, not for the MM1.
But then the discrepancy is only MM2, right?
Sorry, you mean the?
Discrepancy is MM2.
Sorry, this one is MM1 and this one is MM2.
MM1.
Yeah, the difference of the modeling and observation is only happens in MM1, but they have the we say angular dispersion, like angle difference in both MM1 and MM2, since they have polarization observation toward these two regions.
So then MM2 model on data are weak, right?
Yeah, and that's they think that's only this could only say that the gravity may not very affect the magnetic field geometry at that part.
Very convenient. No, gravity only changes MM1 and not changes MM2.
Gravity changed the large scale, but they do not cause the small scale perturbation.
Okay, so I guess my question is why is the difference between model data in MM1 but not MM2?
Oh, because MM1 is much massive than the.
How much?
They also calculate the mass of these two regions. Let me check. Here, MM1 is 2.3 times more massive than MM2.
Okay, let's stop there too. Okay, please go ahead. Thank you
Okay.
very much.
So we just say that there's a quite strong magnetic field strength, but still cannot prevent the fragmentation. So they think that back to this figure two, they think it is aligned with the observation because in G333 they did not found any evidence of rotation in the envelope region, which may caused by the magnetic braking. And they also found no significant outflow signature coming from these two protostars. And this is consistent with overall physical scenario of very weak outflow and no disk on the strong magnetic field strength. So they want to confirm that their observation is aligned with this strong magnetic field. Okay, so that's all about their paper. So their summary, their work shows the magnetic field toward G333 is very strong enough to stabilize the environment toward the center. And a low magnitude of turbulent to magnetic energy ratio indicate a suppression of the magnetic field over the turbulence in this region. However, gravity is much larger than this too, so yeah. It's a summary.
So let's go to questions and comments. What's the overall picture? So, okay, this is pretty nice result, but then where is the overall picture? Where is this field is going? They keep observing one by one, and then where is it going?
It is not very sure the what's the role of magnetic field in this massive star formation. So at least in this paper, they confirm that if there's a strong magnetic field strength, then which may cause by no rotation and no outflow and something else, like this thing. So if they observe different massive protostar, they may found like magnetic field can do other thing or confirm with the theoretical model.
Okay.
Yeah, I think this is the direction of this field.
Okay. So if you have huge amount of armor time, say if you're king of the armor, how many more of them you observe and then you can conclude?
More time like observe different region.
Okay.
Yeah, and found if this result is consist with all the protostar.
All the photos.
Yeah. Like if it has a weak magnetic field strength, then if it's still with no rotation, if it will have larger rotation or it will have the same result like this.
Okay. Okay. Any other question, comments? Okay, good. Then thank you, C-Team. And then shall we go to Jefferson?
Yes, I share my screen.
Okay. Already half the semester, so please try to be more active.
This is my third one, right?
I don't know. Okay, sorry. This is third one, yes.
Yeah, because we have some like typhoon or something.
A little bit, but then I will still suggest to be more active. Okay.
Okay, So I posted this paper in Facebook just before. So
Okay.
yes, so this paper is about to find over-density region of galaxies at very early universe. So using JWST data. So in general, so people want to understand the galaxy evolution and formation scenarios in the long history of the universe. And then many people wonder how this galaxy environment, say there are so many galaxies, and in such environment, this may affect the evolution of galaxies. So therefore, how this environmental effect works in terms of galaxy evolution. So to understand this, finding high density, over density regions in the universe is really important. And then, especially at high redshift, to understand whole picture of this galaxy evolution. And then in this work, so they try to find over density regions of galaxies at redshift between about 5 to 9 using JWST data. Then I don't know, but then probably they confirmed probably one of the highest or highest redshift of over density regions, which is more than redshift H. And then point is, I think they combined Hubble Space Telescope data, imaging data, and also JWST photometries, image data. And also they use slitless spectroscopic data taken by, again, JWST. And then for some galaxies, they really have spectroscopic confirmation of redshift. And then using this JWST field, which is in good north and good south field, I think they found 17 or so. 17. Okay. They found 17 significant galaxy over densities in these two fields in sky. And then one of the highest, maybe two highest redshift spectral confirmation is redshift about 8 or 7.954 and 8.22. This may be the highest redshift confirmation of over density in early universe. And then they also estimate their halo mass. And then basically this over density region at very high universe should be counterparts of largest, how to call this, largest galaxy cluster at local universe. And then let me going. As I mentioned, yes, they use a JWST data in good north and good south field. These are basically provide photometric data. And they also try to combine slitless spectroscopic data in these two fields. That is this one. I'm sorry, I didn't know this one, but Fresco. I think this can provide slitless spectroscopic capability. So that means they can take a spectrum for many sources in the same field. So then, let's say they have photometric redshift and also spectroscopic redshift for galaxy sample observed by JWST. And then maybe I can go this figure. They can check for majority of the sample, they do photometric redshift, so therefore, which is shown in vertical line. And then they can select sample which has both photometric redshift and spectroscopic redshift. So therefore, they are checking this how photometric redshift is accurate. So this is photometric redshift as a function of spectroscopic redshift. And then basically, they looks okay. So they are aligned on the one-to-one relation. So therefore, let's say their photo-z is okay. Then based on this, they try to find over density region, which is usually they call proto-cluster candidates, I think. And then I'm sorry, I didn't read the details how to identify over density, but they identified these over density regions at very high redshift, ranging from 5 to 8. And then this is a spatial distribution of individual over density regions. So I think they have this distribution of over density region. But anyway, and then I quickly go this one. They have a individual photometry. I mean, they have a photometric data and spectroscopic data for individual galaxies. Therefore, they are able to estimate both stellar mass and star formation rate of individual galaxies. So therefore, I think they are showing these measurements for individual galaxies, which are shown by gray dot here. And then again, this is maybe a so-called main sequence of star-forming galaxies. And then they presented this one at very high Z. So for example, in right panel, so this sample includes redshift up to, I'm sorry, their sample is gray dot, sorry. So therefore, their sample should include up to 9, redshift 9 or so. Therefore, this is, I think, very new. And then maybe this is the interesting figure. So they identified high density region, over density region in good north and good south, which are shown by red and green dots here. And then this figure is halo mass. So now you are finding galaxy clusters or proto-galaxy clusters. So therefore, they can calculate the halo mass of galaxy cluster in y-axis as a function of redshift. And then they estimate the halo mass for their sample assuming stellar mass to halo mass ratio. I think they use an empirical ratio between stellar mass and the halo mass because they have a photometric data of individual galaxies. They should be able to calculate the stellar mass. Then they convert the stellar mass to halo mass, assuming certain ratio, empirical ratio. And then, therefore, they can basically calculate the halo mass for their samples, their overdensity samples. And then, this gray dot ones, they are universe machine. Basically, this is a model. They say a semi-empirical model. So anyway, I think there's a model right, of this cosmological galaxy formation. And then they provide this cone data. So therefore, using these galaxy models, they can do the same analysis to this simulated model galaxies. And then they can also identify overdensity in model or galaxy sample. Then, which is shown by gray dot here. And then, basically they are saying this model prediction shown by gray dots are consistent with what they found from real observations, which is a colored dot here. So therefore, they found a good agreement, I think, between this universe machine, model prediction, and observations. And then what's nice about these clusters is, I think they found the highest redshift over density here, beyond redshift 8. And also this is confirmed by spectroscopic data. I think that's new in this paper. Then again, maybe last point is, because they are almost massive ends of galaxy halos, so therefore they are supposed to become the largest galaxy cluster at the local universe. And then theoretical prediction of this evolutionary trap of massive clusters is shown by this yellow shaded region. I don't know why they have offset here. Probably halo mass estimate is different between these data points and also this theoretical prediction maybe. But anyway, even though there's an offset here, well, they should be supposed to be the massive end of galaxy cluster. So therefore, they expect these guys are actually progenitor of currently largest galaxy clusters at redshift 0. So I think that's all from this paper. Is that okay? Sorry, I cannot hear you. I'm sorry. Maybe I cannot really hear you. Hello.
Any more questions, comments?
Sorry, are you asking? I'm so sorry. Did you hear me?
Yes, yes.
Okay. I'm sorry. I didn't hear you while I'm speaking. I'm sorry.
Okay, no problem, no problem. They didn't show the image of the cluster. It seems they don't.
Seems not. I don't see image. Seems no.
Okay.
Hmm.
They need it for newspapers, I think,
Really?
if they want. I think.
Yeah.
Okay, that's a very good paper. Yes. How did they identify overdensities? Did they show how many sigma? Maybe I missed.
I'm sorry. I didn't read. I'm sorry. But I
Okay.
think I thought they are comparing with random density.
Okay.
I remember they described somewhere. This one maybe density around 6 to 12 times that of random volume. So probably they are taking ratio.
Okay.
Maybe similar to Cosas density estimates.
No, they just calculate the density.
Okay. Thank you.
Okay. Any other questions? Yes, please. Someone?
You mentioned about something like discovery of galaxy cluster at high redshift using this data.
Sorry. Initial part was I didn't hear you. So I'm sorry. Could you repeat it again?
Did they mention about maybe something like galaxy cluster discovery on high redshift using this data? Because the overdensity must be something related to that.
I think basically they are saying this is a proto cluster.
Oh, it's protocluster.
Proto cluster because usually when people say galaxy clusters, they remember galaxies a lot, right? More than 10 or 100 or so, right? But at high Z, I think structural formation is not going so much. So therefore, number of galaxies included in overdensity is small. So then they call it protocluster. So,
Okay, so yeah, at that redshift cluster is not formed perfectly, I think. Yeah.
I don't know boundary between cluster and protocluster, but I think they think this is a progenitor of galaxy clusters at lower redshift. Yes.
Yeah, I think from this we can know when the how is the evolution of the cluster from the protocluster until like the galaxy cluster we observe at low redshift.
Right.
That's a good point.
I think they really want to draw that kind of storyline observationally. I think so.
Okay, good question. Any other questions? Okay, if not, maybe time to stop. Who wants to present paper on Tuesday next week? Oh, amazing. Very, very, very active. So, Suyon, right? Then, lot of people, a lot of people. And then, Incheon, is that right? Chongqing. Chongqing. Oh, okay. And then, yeah.
23 is Wednesday, so
So we already fill in the spreadsheet.
What do you mean?
22 is Tuesday.
So
Oh,
we already fill in the
by
spreadsheet.
yourself? Okay. So we have in Sony, right? So oh, and then summer and then see you.
Early.
Is it right? Okay. Business, I'm sorry. They already filled it by themselves. So business, can you do it on Wednesday? Is that possible?
I think Yuri-san raised the
Oh,
hand.
I'm sorry. Is it Yuri-san, not business?
No, it's Yuri.
Yuri-san, could you do it on Wednesday?
Okay.
Thank you. So Yuri-san on Wednesday. Okay, very nice. Very active students. So thank you for speakers today, and have a good weekend, and then see you next week.
Thank you. Bye.
Yep, very nice. Young students are very active. Very good.